Testing one, two. All right. Hi, everyone. Welcome back to the stream. Thanks for joining. Um, so on this stream, I'm going to be building a rendering engine in Haskell using Vulkan as a sort of rendering library. And yeah, we're just going through from the start. So we're streaming here on Twitch. All of the previous streams can be found on YouTube at Sam Bennett underscore TV. So you can see the previous streams here. So our goal is sort of to produce something we can use to easily experiment with different like rendering techniques, different render passes, um, things like physically based rendering, that sort of thing. So we want our rendering engine to be somewhat general, as in like we can express different kinds of render passes easily, different kinds of rendering techniques easily. So we're not building a specific purpose renderer for a specific kind of game. If that was the case, we might go about things differently. But yeah, we're keeping like a kind of open mind to our sort of uh, interface to our renderer. So to get started, we'll talk about where we were last week. So if we open up our triangle example, so we've taken a few steps back. Um, oh, cool. Actually, I think I know what's going on. First thing we're going to do before we do anything is update this. Yep. Okay. Next flake clock update input. Next. Uh, you have to forgive me. I have an interesting issue. So, um, I need a specific commit and great. Okay, now we can get rid of this and no, don't do that. Yes, so I have this program called RenderDoc. I didn't write it, but we have this program called RenderDoc that we can use to debug issues with uh, the whatever rendering, Vulkan rendering we're working on. And there's kind of this interesting interaction where I need the glibc version of my computer to match the glibc version that's used to compile the program, which is kind of unusual and weird, but it's because RenderDoc is doing some dynamic loading of dependencies. And so they just need to match up. So that's what I'm doing here is just matching up the glibc versions of my computer and this project. Um, it's kind of a pain. And the reason I'm pinning it to a specific version is because these things take forever to build. And I've already built this version. I did do some things last night to make sure the stream went smoothly, but I didn't foresee this issue. So yeah, we'll wait for this to go. But um, what are we looking at? So this is our current triangle example. We are doing some stuff like beforehand, and that's what this inner example thing is. So we're loading our shaders and setting up our passes, and we've got this all in an acquire structure, which we have introduced before. So if you have a question about that, just or want to know about that, just put it in the chat. But otherwise, we'll head on. Then in our main, we're creating a window and allocating Vulkan context, allocating some of our rendering primitives and like our swap chain. Oh, excuse me. Uh, and yeah, then we're kind of doing our, doing a whole rendering loop. So we're getting the next frame and we're presenting it and allocating a command buffer and recording data and handling events, that sort of thing. So what we kind of decided, what I've decided that we want is more of a just declarative, and yeah, declarative, I would call it, interface where we can say like, okay, give me a vertex shader, give me a fragment shader, and like here's a subpass, and blah blah, and it gives us back a handle, but it doesn't necessarily like create that thing at that instant. When we call with VK shader module, it's basically like for all intents and purposes creating it at that instant. Um, Whereas we want kind of the ability to collect all the information about what the user wants, and then more efficiently like instead of just allocating one at a time, we could allocate 8 things at a time. For example, if the user asks for 8 vertex buffers, we can make one big allocation rather than making lots of small ones. Um, that's the primary motivation. Uh, but one more thing I'll do. Get rid of that. Try that again. So yeah, we want to do that. That's going to take kind of significant changes. It's going to set us back a few steps. So um, we're going to lose our triangle example, but we're going to get it back and then get back the next example, and we should be good to go. So, what does it look like? It'll look something like, we'll get rid of this code. And we'll start. So, we're still going to need to create the window and the VK context. Excuse me. But instead of creating all of these rendering primitives and doing all this stuff, we'll keep the event loop for later. What we're going to do is create a renderer. So we'll create a renderer, and that's going to hold a lot of rendering primitives and do like the acquisition of a frame for us. Okay, cool. Looks like we've got our environment. That's good. I'm just going to quickly add tissue so I'm not like sniffling on stream. Give me a sec. All right. Yes, so we're going to create a renderer instead, and that's going to hold our frame primitives, our renderer primitives, like our frame in flight, and all of the syncing and all that kind of stuff. Um, so then we'll do something like this, where we create a shader. So we call this function called shader. It takes the renderer and it we tell it, is it a vertex shader or a fragment shader? Tell it what the entry function is, and then we tell it where the data is. And this type is an acquire, like lazy byte string. And so what that means is, so acquire is like that type that says, this is how you like acquire me, but like you don't have to do it right now. Like, so we're not actually reading the file here. We're just telling someone else how to read the file, how to get the shader data. And so that's kind of this idea of like deferredness or laziness, where we're just deferring um, things like loading the data into a later point in time. And that allows us to be more efficient and allows the user to like care less about what's going on. Um, they can care about what they want to care about, what's important, and we can care about all the rest. So we create a render pass layout and create some a subpass or pass. So I'm just copying this stuff because we went through it a little bit in the last stream, and so I'm just kind of copying it from there. So and you've already seen the subpasses. So this is a very simple triangle example. So all it is like a vertex shader, a fragment shader, which have hard-coded values for the vertices of the triangle, and we've got a single pass. Then we're going to go ahead and create a function to render. So given the renderer, we're going to submit uh, some draw calls. So there'll be um, a single draw call here. Every frame, we're just going to have a single draw call, and that's just going to draw 3 vertices using the subpass, so using that shader. And then our loop from before, get it in line. So this is how it's going to work. Cool. So yeah, then we got our render event loop. So our event loop is going to like do the render step and then handle some events, and if it should continue, it's going to go again. Cool. So this is what our triangle example is going to transform into. Um, there's quite a bit less code in this kind of iteration, so that's good. It's more concerned just with the render pass, and that's really the kind of interface that we want to make. We want to make one where we can like easily experiment with different render passes and different rendering techniques. And we don't really want to care too much about, you know, getting the next frame and doing all of the bookkeeping. Um, we'll take care of that in the renderer. So this will be our triangle example, but it's not going to run because we don't have this kind of stuff. So just gonna get these in line. So what are we gonna add? We're gonna add a render pass layout. handle to 1 and subpass index. What is the index? Like a word 32? That'll do. Blah, blah, blah. The types. In our draw, we're going to add draw subpass. So handle to subpass. Let's add this idea of a render pass layout. So typically, like in Vulkan, we have this idea of like render passes and subpasses would typically be like, here's my render pass and here's like, my 8 subpasses. We've kind of like inverted that a little, like not really inverted it, but we've just inverted the way you declare it, where you instead say like, this is my render pass layout. You don't say which subpasses it has, but then in each subpass you have the subpass point to the render pass. It's really neither here nor there. We might change it in future, but it just seemed to make more sense for this declarative style. Otherwise, you're declaring all these subpasses, and you're kind of declaring them in the context of a render pass anyway. But yeah, because anyway. So what is a render pass layout? So like, this is the info that you use to create the render pass, and at the moment we just have nothing because we just like hard code that. But in future, this will be things like your attachments. At the moment, we just say you have one attachment, which is the swap chain image view. But yeah, in future, you'd have like other attachments, like this is my position attachment, where I'm going to record the position of all of the fragments. Yeah. But the render pass layout, even though it's hard coded, even though it's not configurable, it's still made up of a Vulkan render pass and some frame buffers. So even though each render pass is hard coded to just have one swap chain image view, there are multiple swap chain image views. So for a single render pass, we create multiple frame buffers for each swap chain image view, saying like, okay, frame buffer 1, you've got swap chain image view 1, frame buffer 2, you've got swap chain image view 2, etc. Okay, so we're using handles now, so we're gonna change this to handle. We'll leave this as is. This is correct. Yep. I'm going to get rid of this render pass info. It's the old style. And when it comes to subpasses, I'm going to get rid of the draw. Kind of divorce the idea of the subpass having the draws encoded beforehand so that we can like dynamically change it. Get rid of that stuff. We're not using that anymore. Doing things differently. Okay. Leave all that as is for now. Okay, when it comes to handles, we've got our shader and our buffer handle. And we're also going to add a render pass layout handle. Gosh, it's a bit wordy. So that's going to be like a deferred computation from render pass layout to release key render layout. From render pass layout info to render pass layout. And the reason that we have the release key here is because whenever the swap chain gets recreated, we're going to need to delete the old render pass, create the new render pass. So we're going to need the release key in order to free the old one. There we go. Oh, that's a shame. Okay. And we're also going to need a subpass handle. Excellent. Okay. Hmm. Just going to give myself a little note. Just some thoughts I've had. Get back to it. Okay, so the last thing that we need to do is change the renderer itself. Oh, and of course, we'll need to import all of this. Oh, now we'll get back to that. Okay, yes, so we don't have a renderer at the moment. So we're going to go ahead and create one. Like I said, this is going to take care of all of the bookkeeping. So the swap chain and the frames in flight. So essentially our frame synchronization. Should probably rename that. Frames in flight, sort of confusing. We're going to keep a list of our render pass layouts. Um, so that when we recreate the swap chain, we know what we need to recreate. So we need to recreate all of the render passes and then all the subpasses. And maybe this isn't the best way to do it, but it's just simple for now. And we're going to pass in the device. So we're going to get the device from the context and let the renderer hold on to it because so many of its operations use the device. So create renderer. Um, so, so we'll just copy most of the stuff from our previous code. So we're just, everything's going to be the same. We're going to like create the swap chain the same. We're just going to put the swap chain in a variable now, or a thread safe variable. Still going to create frames in flight. Then we're also going to create a queue for the layouts. You can think of it as the Vulkan render passes, and a queue for the passes, which you can think about as the Vulkan subpasses. TQ and here renderer swap chain var frames in flight layouts queue passes queue, and then grab the device from the context. Perfect. Let's see if we can get this to compile. Yep, all this is gone. I need to import a whole bunch of things. Just going to delete some old functions. Import some more things. And we're good. We're just going to get rid of that buffer example because we don't expect that to work, or the uniform example to work. Because we've changed all our fundamental rendering types, so can't expect that to work. Cool. Then just got some old things here. And we don't need that. Just need things like subpass and shader and render pass layout. Submit. Cool. Go back to that. So we'll go through these initial, brainstorming that we did. So we're just going to pass in the renderer to each of these examples to keep the interface consistent and give us kind of options in future. In this case, with the shader, we don't actually need the renderer, so we're just going to ignore it. But it's likely that we will in future. For the buffer, same thing. We don't actually need it right now. Now we're going to create a new one for render pass layout. And same sort of thing. It's going to take the renderer as the first argument, and it's going to return a handle to a render pass layout. So just like everything else, we're going to defer a computation. In this case, we just pass in the hard-coded render pass layout info. But we are also going to write this handle to the TQ so that we know all of the render passes that we have to recreate when the swap chain goes out of date. So like whenever the window is resized, basically. Go ahead and import all of this. Yep. Write TQ and STM import qualified as STM. Okay. So there's the render pass layout. Now I'm going to do the same thing for the subpass. So write TQ to the renderer passes TQ. And then we are going to return that. Import the subpass handle. Okay. So that's good. Now we have to do a couple of things. We have to teach the renderer how to evaluate that deferred function from render pass info, subpass info to subpass render pass. So let's start with the subpass. It's right here. So eval subpass. This is going to look just like our eval buffer. So just give it a moon end resource for now. Renderer, handle subpass, m subpass. Okay. So we're going to evaluate the deferred computation if it hasn't been evaluated already. We'll make a different one that can that we can use when the swap chain's recreated. But for now, yeah, well, first thing we're going to do is evaluate the render pass layout if it hasn't already been evaluated. And then we're going to go over each shader and make sure to evaluate that as well. So this way we load our render pass and we load our shaders. Now we haven't actually written these functions yet, but we will. So then we're going to do a few things. We're going to create, like if we have a look at our render types, what are we making? We're making a subpass, and so we need a pipeline and pipeline layout. So not too bad. Pipeline layout. This is, we are just going to copy code from our make frame data function that we just deleted. So, yep, we pass in the descriptors, and this is our pipeline layout. So pipeline layout is just about kind of the descriptor sets and the push constant ranges. And we have none of those at the moment. Then we are going to create the graphics pipeline. And a lot of this is just hard-coded. So we just copy all of it from our previous make frame data function. So this is how it works. We get the pipeline shader stages from the shaders. This gives us, yeah, this gives us all our shader stages. Then we create the graphics pipeline, giving it our shader stages, giving it our kind of vertex info. So in the subpass info, we've got vertex input bindings and vertex attributes. They get put here. Our input assembly, which we've hard-coded to triangle list. We can make that configurable later, but we don't care about it right now. Test solution and viewports, we make them always dynamic, and blah, blah, blah. All of the rasterization state. We'll make this all configurable when we need to. And finally, the subpass index. Then this gives us a pipeline, and we are gonna return that. So pure subpass pipeline layout. Great. And then we'll return the pass. So there we go. Should import this. And this doesn't exist yet. Cool, so eval shader. I think we might have already written that. It just doesn't take that argument yet. Yeah, so cool. That should fix the shader problem. And now we need our eval render pass. So again, this is most of the code is just going to be copied from before. All we're doing differently is we're making it a sort of deferred computation. So Just give it a main resource. So we take a handle, render pass layout, and we return the render pass layout. It's going to be very similar to before. Because, well, we've got this render pass info here, but it's got no information in it, so we can just ignore it. Hmm. You know, I reckon. Okay, let's instead of passing in the renderer, let's pass in the device, and we're also going to need the swap chain, so we'll pass that in as well. Okay, cool. Oh, this is layout. Okay. So with VK render pass device, then we're just going to copy all the stuff from our previous example. Yeah, so nothing's changed about how we make the render pass, which is why I'm copying it. So device, all right, cool. So we are setting up a single attachment, which is just the swap chain attachment. The subpasses are all like hard-coded. The dependencies are all hard-coded, and the frame buffers are created from the swap chain image views. So for each swap chain image view, we create a frame buffer for this render pass with the right attachment in the right order. And then we're just going to return a render pass layout with our render pass and frame buffers. Okay, so that should be good. Oh, name this like L or something. Cool. Now we're going to change this to have a similar type and swap chain. Cool, just a little bit of modification there. One 60. Hmm. Oh, okay, we need some mask. I'm gonna add lift IO. What's going on here? shader stages. Uh, Red mask. Okay. Alright, so that looks like that's good. Let's just take a look at my notes. So we shouldn't be far away from the triangle example now. Ah, yes, but we have to do the whole draw part. That's kind of important. Okay, so what's this going to look like? Submit. So, given the VK context, renderer, the list of draws, we're going to do something. So the first thing we're going to do is read the swap chain. So we've got it in a variable at the moment. We're just going to read the current value of that variable. From renderer swap chain. Cool. Just put that at the end so that we... Cool. So then we get the drawers. Yeah, lift AO, get drawers. Probably doesn't have to be IO. Yeah, we'll give that a go. Yep. Okay. Here's where things get interesting. So, we're going to get the subpass. Oh, yeah, for each draw. Going to get the subpass, and then get the subpass info. We are going to evaluate, we get a render pass basically. So we eval render pass, sorry, draw subpass. Layouts, giving it the dot renderer. Don't even need, we can just be like VK device context. We also need the swap chain and subpass info dot layout. Great. Okay. Import get seed. Okay, so we've got ourselves the oh, we gotta add a few things. Cool. Got ourselves the render pass for that draw. We've got ourselves these. We gotta get the subpass pipeline. We don't need the pipeline layout at the moment. eval subpass, R subpass. But this actually takes the VK device and the swap chain. And it's going to need unleft IO. Cool. Now, so what we've done is we've made sure to create the render passes and the subpasses, and we've returned them. And maybe if they've already been created, nothing would have happened and we just return them. But if they haven't been created, they'll be created. So that's kind of that deferred laziness. Yeah. So now we're going to do all the bookkeeping. So we're going to get the next frame in flight, which is our frame synchronization stuff. VK device, context, renderer frames in flight. And yeah, frame in flight. Don't need the descriptor pool, but we do need the command pool. And run resource T to, okay. Now we get to copy all of our draw code. So yeah, the draw code's exactly the same. It's just where we're getting everything from is different. Okay, so just quickly go over it. Make sure to indent it one more. So, what's the matter here? Pass error. Hmm. Just import these things. Okay, so for each draw we are getting stuff and then oh, this is not gonna work. Well, not well. Okay, so first off we should evaluate everything for each draw. Cool. So the reason we're doing this here is so that any like thing that we create stays in like the monad resource context. So it's like still stays created, basically. Um, then we get the next frame of flight and we get, the command buffer and here's where we go through each draw. So should probably have some way of getting this unsafely. me a sec. So we'll just create some way of getting the result of the deferred computation. Like we know we've already evaluated it, so like there's no need to try and evaluate it again. In fact, we'd rather just error. And I'm not super happy with this whole thing, so with that whole like deferred computation thing, so um, hopefully we get something better in future. Um, but we'll work on that. So we'll go unsafe get handle, and we'll go draw dot draw subpass. It's going to give us the subpass. So that's made up of the pipeline and the pipeline layout. And we'll also get the render pass layout. And that's made up of the render pass and the frame buffers. Draw dot. Oh, actually, this is. What did we have before? Yep, so we need the subpass info because we need to get the render pass layout handle. So subpass info dot layout. There we go. Okay. Now from the frame buffers we can get the right one and then set up the render pass and draw. So at the moment we're being very naive. So we're starting a new render pass for each draw um, and doing all of that. When really, like, we should probably group the draws by render pass, and then start the render pass for that group, and then, make all of the um, calls, and then do that. But it's no big concern. We will, fix that later. For now, we just want a working triangle. So yep, we are only submitting one command buffer though. We begin the command buffer before the draws, record all the draws into that command buffer, and then submit. But we've only got one draw at the moment, so no need to worry. Oh, looks like we're missing an import. And render triangle. Cool. And BSL, yep. Import byte string lazy. And looks like that's working. Oh, the compiling at least. We're going to discard that. And fix the warnings here. Okay, let's load our triangle example. And oh, yeah, we're missing. Let's get rid of this. Just say vector.empty. Great. So yeah, the validation layers aren't working on my computer at the moment, so to fix that up. But yes, we've got our triangle. Oh, lost that. Cool. So yeah, we've got our example like working again, which is good. Back to seeing stuff on the screen, great. We've got like a nice sort of like declarative sort of interface um, for specifying essentially the render pass that renders this, which is nice. It's like real small. It's not much code at all. Um, but we have made some compromises. So when I say like resize the window, it just crashes. And you can see that there's a swap chain out of date exception. So we might have the interface how we like, but there's still some work to do in the back end to kind of get back to where we were. So the reason this is happening is because when we resize the window, um, this present function, it's gonna acquire an image for us, and if the swap chain's out of date at that point, it's going to throw an exception, and if it doesn't there and it goes to present later on, and that throws a swap chain out of date exception, then like this is also going to throw it, and there's nothing to handle it at the moment. So we have no code handling that swap chain out of date exception. And when we do, we want to do things like recreate all of these render pass layouts so that they're still up to date. But for now, we'll just say um, that we have got a working triangle example. We'll commit that code. So, missed anything? No. So we'll call this working triangle example. So commit that. So you can go see these commits at github.com sambnt/rort, R-O-R-T. And there we go. So cool. Well, that's step one. So step two then will be getting the swap chain resizing working. Um, but I'm going to take a quick break, a 10-minute break, and then we'll come back and get to work on that. Thanks, guys. I'll see you soon. We're back. Thanks everyone for joining. So, in this series, we're creating a renderer in Haskell using Vulkan as our rendering library. And we just got our triangle example working again, but we have problems when we resize it. We get a swap chain out of date exception and the program crashes. So, we're going to create a module to look after our swap chain. So, we'll call it swap chain images. And we'll get started. So the swap chain images data type is going to hold our swap chain in a variable. It's going to have the images, and that's going to be a queue of swap chain image. And we'll get to the other bit. So we'll import these things. Now, kind of explain what we're trying to do here. Rods, render, swap chain. Swap chain. Oh, what's happened here? No. Why did you do that? Okay. Cool. So, what is a swap chain image? Swap chain image is an image index. So this is the index of the image in the list of swap chain images. So swap chain has many images, and this is one of them. And then it's got a copy of the swap chain. Now, because it's Haskell, it's probably not an actual copy, which is kind of what we're relying on. But let me explain this. So if we have the swap chain in a thread variable like this, that means that multiple threads can access it, but there's like a chance for contention. So if every frame, which is what's going to happen, every frame, the submit function or the render, the frame function is going to need to get the swap chain. So it's going to need to read this mvar and find the swap chain in it. And if we have like 3 of those threads happening, that's like a lot of contention, and it's happening every frame, which is just not great. So what I'm doing is creating like a queue of these swap chain images, and they've got a copy of the current swap chain in them. And when the swap chain changes, we'll like clear the queue and add in a bunch of new swap chain images that have a different swap chain reference. And that way, like, I'm hoping to reduce contention. Actually, I haven't measured any of this, so maybe I shouldn't bother, but whatever. The other thing we're going to keep track of is which images are out at the moment, so which images are in use. And it'll become obvious why we need this in a bit. So I'm going to write a little comment here. We copy the swap chain to each frame so that each thread acquiring a swap chain image doesn't have to contend with other threads to read the TM var. We know the swap chain will only change when it's recreated. So essentially there's just like no need to always be reading the swap chain variable when it's only, we kind of know exactly when it changes. Yeah. So let's create one of these. So the swap chain creation is the same as we have in the renderer at the moment. So we'll just copy that code over. Great. And then we'll make the swap chain images from the swap chain. And then for each, do an STM transaction, create an image queue, return it, and in between, I'm going to write each of the images to the TQ. Cool. And then we'll return swap chain images, swap chain var, image queue, image out queue. So we'll need to make an image out queue as well. Okay. Clear up these imports. Import, actually. Just a bunch of imports. Okay, let's write this make swap chain images function. So it's going to take a swap chain and return some swap chain images. Pretty straightforward. We're just going to fold over each of the images and give it its current index and the current swap chain. So zip 0, so make an infinite list, and we'll zip it with the image views. That'll give each of the image views an index, which we then pass into this function, which will create a swap chain image. Make sure to image views, import that, and to list. So this converts the vector to a lazy list, which lets us zip it lazily with an infinite list. That's important. You know, if we tried to convert this infinite list to a vector instead, then we'd get a infinite recursion, because the vector will try and like strictly evaluate all of that infinite list. So that's good. Great. Let's add this to like a bar file. Swap chain images, and we'll give that a load and see what happens. Cool. This looks okay. Now let's add a function to acquire one of these images. So swap chain images, swap chain image. So the user will give it a function to take a swap chain image and return a result. And what are we going to do? So these are the images. Here's the function to call. So we're going to acquire a new image and let the swap chain images know it's like in use or out. We should call this maybe in use. So we're not actually recording which images in use, are just the number of images that are in use. That otherwise we're like having to like read the queue to like make sure that the indices like match up, but we don't really care about that. We just care about that all of the images have been returned. We don't care about like which image in particular. So let's acquire that image. So we read tq dat.images. So that gives us an image. We're going to write to the tq. Oh, actually, we can do this easier. So we're going to let the sort chain images know that we're using an image, and then we're going to read an image. Do that in one transaction. And then we're going to try the users function. In case the result of, so in case we get an exception, we're going to do something. But in the case we got a result that's successful, we'll write the image back to the queues. So write the tq images dot images in use. Sorry, we'll read from the tq. So we'll take a value back from the images in use to say like, okay, one image is no longer in use, and then we'll write back to the images available, and we'll give it back the image that we took. And then we'll return the result. What have I done wrong here? As far as I can tell, nothing. Oh, okay. Never mind. Let's add try. Oh. Cool. Okay. So in the case of an exception though, what are we going to do? So what we'll do, we'll definitely always write back that an image is back. So it'll no longer in use. So stm.read tq images in use. So we'll say that this image is no longer in use. Great. Or a image is no longer in use. But if it's a swap chain out of date exception, then let's not write back the image itself. So we'll do this, but if it's a swap chain out of date exception, we won't do this because we know that image is no longer like acceptable. It's no longer usable because the swap chain's out of date. And then we'll rethrow the exception. Okay, what have I done wrong? Monad, we'll just import some things, unless, and swap chain is swap chain out of date, and throw IO we'll add to this. What's going on here? This I don't understand. Okay. Do couldn't match expected type STM with actual type. Right TQ. Oh, there we go. Okay, redhead catch. Great, there we go. So don't return the swap chain image when swap chain is out of date. It's not usable. So yeah, we're telling the swap chain images that, look, we've returned an image but it's not like usable. So another thread won't pick up that image. But we've let the swap chain images know that we've returned returned a image, because what the swap chain images needs to do is when it's asked to recreate the swap chain, it needs to wait for all of the images to come back, because otherwise it's going to recreate a swap chain that might be in use, which is what we don't want. So that's the whole purpose of this TQ. And yeah, we just, to keep things kind of efficient, like we're not going to return the swap chain image here, because then another thread might pick it up and start using it. And like, there's a million ways to do this, right? Like we could have the little variable that we set that's like is recreating or something, but I don't want the threads to always have to contend over this same variable as much as possible. Cool. So our last thing we need to do is recreate the swap chain. Let's just start like this. So context, images. So we'll try and take the ember that has the swap chain in it. And that way we kind of claim ownership of the swap chain. Actually, there's something I didn't address in this last thing. So what happens if we get this image and then we get an exception here, like an asynchronous exception? Then what we've done is we've claimed the image, but we haven't written it back. So we've talked about this before, but we should mask asynchronous exceptions here. And add monad mask. Cool. So if this throws a synchronous exception, it's fine. The guarantees of STM, essentially, like if this throws an exception, then we haven't actually done any work, which is great. Then we'll restore exceptions for the kind of period of time of the user's function. Restore asynchronous exceptions. And then if we get an asynchronous exception here, or a synchronous exception in this user's function, that'll get returned to us as a result. And then we can sort of pattern match on that result and be like, okay, here's an exception. Let's return the image and possibly also return, well, make sure that an image is no longer in use and possibly also return the image, and then rethrow the exception. So that should happen quickly, like none of this should block. Otherwise, we're all good. So we'll just make that asynchronous exception safe. Great. Like, I suppose this is actually interruptible, but neither of these should block, so I think we'll be fine. And by interruptible, I mean, what we've done is we've masked asynchronous exceptions, so if we get a thread kill exception, we won't get killed, but what mask doesn't protect you from is that some of these interruptions might be interruptible, which means that if they block, the runtime system might just interrupt them anyway. But reading a value from the TQ, just think about this. If we have more threads than we have images, they're just going to block anyway. Like they're going to block here. So we should be good. We'll see. So anyway, back to this. We're going to try and take the M bar. So we're going to try and claim it. And that way, we want to try and stop any work that's happening. Well, not stop, just wait for any work that's happening and prevent any new work from happening. So if we try and claim it, but it's already been claimed, we'll just say like, okay, someone is already working on recreating the swap chain, do nothing. So some other thread has already started work on doing that, so we can just exit. Now, if we do get the thing, we got the swap chain, then we're going to make sure to mask our asynchronous exceptions because we're going to do some stuff. We really want to make sure that at the end we either return a new swap chain or the old swap chain. Ideally the new one, but if we get an exception, we return the old one. So let's create a little thing, new swap chain from old. Just a little function. It's going to clear all existing images. So if there are any unclaimed images in the queue, like so swap chain, outdated images, we know they're outdated now because someone's asked us to recreate it. We'll just clear those. So we'll just flush the queue. STM flush TQ and then the images. Then we wait for all images to be returned. So at this point, every thread is going to be getting swap chain out data exceptions. So it's going to be returning the images out, but not the images themselves. So this could definitely block. So we're going to restore exceptions for the... Oh, should we? Anyway. So yeah, we're just going to wait for the images to be returned. And we'll just throw an exception if we get like blocked or there's an asynchronous exception like a control C or a thread kill. I'm going to be respectful of the need to clean up quickly. So then we're going to create the new swap chain and free the old one. So first we create a new one and we make sure to pass in the old one as an argument. So I'll just copy that from other work that we've done. So yeah, we're passing the old swap chain as an argument. Then we release the old release key, and then we return the new swap chain. There we go. So now for thread safety, what I'm going to do is we're going to call this function. Oh, gosh. Having a stroke. New swap chain from old, but on exception, I'm going to make sure to return the old swap chain. So like, if if we get an exception here, we haven't actually created a new swap chain. We have flushed the images though, maybe we should return those. Yeah, we need to do that, so we'll do that. But, like, simply, we need to put the old swap chain back. Otherwise, we're all good, and we can stm.put tmvar images.swapchain, the new one. Make the new swap chain images with the new swap chain, and we'll write them to the TQ as well. And then, yeah, that's it. And go pure. Just like that. Okay, let's add some imports. Keep calling it dot for some reason. Okay, and monad resource. Uh, oh, okay. Cool, so that's compiling. But what did we say? So the first thing we're going to do is we'll put this here. So clear all the existing images, and on exception we'll do two things. We'll put back the old swap chain, and we'll put back the old images. Cool. Yep, we've waited for all the images to return. Yeah, so essentially, yeah, we're just creating a new swap chain from the old and make sure to return the old state if we fail to do that. Okay, monad catch is not needed. All right, let's go ahead and use this in our renderer. So we just create a little module to look after all that bookkeeping. I'm not super happy with it, but like it'll work for now and we can fix it up later. It's certainly better than what we've got. So yes, swap chain images, and we'll import that. Cool. So instead, uh, swap chain images dot create. Well, I think it was the context that we gave. I'm gonna get back swap chain images. I'm gonna pass that in. It's the first argument. Cool. Now, when we go to do our submitting, so we're going to, instead of reading the var, we're going to call swap chain images dot with swap chain image, renderer swap chain. Don't actually, yep, so we'll start there. So yeah, we've got an image that'll give us the swap chain. Then we should be good just to indent all of this. The image index is actually given to us by finally present, so we'll just leave that out. Might not even need that. So, might just add a little note about that. Be here or should. In that case, this would just be a glorified way of handing around the swap chain. Okay, so we've got the swap chain image. Well, we've got the swap chain. And we can do our drawers. I think that'll just work, right? Ah, yes, but the exception. So we'll try this and get a result. So do our whole draw thing and get a result, and then we'll just skip past all of this. And okay, if the result is a swap chain out of date exception, we're going to recreate the swap chain. Cool, recreate the swap chain, add this import. And that should be it. So we won't throw we won't rethrow that exception. Otherwise, if there's a result, well, we'll just call it X. Just return that. So yeah, when we try and draw and we get a swap chain out of data exception, we're not going to crash, we'll just recreate the swap chain. And only one thread will recreate it because we had that thing that tried to take the envar. Um, but yeah, so that actually that should be good. Try, so save, try. Cool. Let's try and load our triangle example again and see what happens. So we've got the window, we try and resize. Oh, and we get a bit of a crash. Oh, yeah. So, give me a minute. Great. All right, we're back. So we got a crash, and the reason is, like, I don't have validation layers enabled at the moment because of just some issues I'm having with that, which hopefully be fixed soon. But the reason it's not working is because we're not actually recreating any render pass or anything. Like the render pass is dependent on the swap chain. We've recreated the swap chain, but we haven't recreated our render pass. So, and another issue is that we only really want one thread to recreate the render pass and stuff. We don't want multiple threads doing that because they'll just create multiple render passes for the same swap chain, which is not great. So when we recreate the swap chain, what we'll do is we'll get the user to also give us a function that's like swap chain to, I don't know, it's just some side effect. So call it after. So after we've done everything, we've got a new swap chain. What we're going to do is restore after and then new swap chain. So essentially only one thread will do this because there's a synchronization happening with trying to take the envar. Yeah, they're gonna maybe create some resources based on that swap chain. So we need to pass in that function. So recreate swap chain, where is that? Here it is. And then new swap chain, we've got some work to do in here. So what does that work look like? Well, let's see. Yep, we'll mask because we're going to be doing some unsafe work. We're going to flush the TQ with all of the render passes in it. Great. And then we're going to restore, going to map over all of the handles and eval the render pass layout. So we'll go BK device, context, and new swap chain, the handle. We'll make sure to return the handle so you get all the new handles. And yeah. Actually, I don't need the new handles. So for all of the render passes, we're going to reevaluate them using the new swap chain. And on exception here, because we've restored asynchronous exceptions. So if we can't create the, can't eval the new render passes, then we'll just write back the old ones. actually. Either way, because the handles don't change, even if the render pass is reevaluated, just like either we get an exception and we write back everything, or we don't get an exception and we write back everything. Doesn't matter either way. Cool. Okay, and then we'll do the exact same thing for the subpasses. So we'll call them PS, PS, PS. The renderer, what is it? Not layouts, passes. And the renderer passes. And instead of evaling the render pass layout, we eval the subpass. Okay. Make sure to import what we need. What's going on here? Yeah, we just need a void. Okay. Cool. So, on the uSwap chain, we're going to recreate or reevaluate the render pass layout and the subpasses. Simple. But we have one issue, which is that eval render pass layout and eval subpass layout, for that matter, they only evaluate if empty. So we're going to have to make a new version that will just always evaluate. And we'll just call it when we recreate the swap chain. So, we'll have to refactor some things because let's just have a look at blah blah blah. So we're going to take all of this stuff and we'll refactor it into its own function called acquire render pass layout because it doesn't change device swap chain. And a handle. Oh, sorry. No, we don't need the handle. So we'll just indent this correctly. This is just common to both, so we'll just refactor. So in the original one, it's the same thing. Acquire render pass layout, device swap chain. Simple. And then we're going to make a new one, and it's going to always eval. And in case there's an old, like there's already a value there, what's it going to do? It's going to, in case there's an old of nothing, then we'll just do nothing. Actually, we can just use, oh, never mind. But if there is something there, like an old value, then we're going to release it. So we're going to make a new one, but if there is an old one, we'll release it. And this, need to import. So this is going to get reevaluated every time that it's called, which is why we only call it when we're recreating the swap chain. Cool. So we're going to go eval render pass layout. Bam. And now we do the same for the subpass. I'm going to take all of the code in the allocate acquire block. blah, blah, blah. Call it acquire subpass device swap chain. Indent all this correctly. It's a lot. 2. Cool. And acquire subpass device swap chain. Oh, we don't actually need the swap chain now, so we can just go device. Sec, yeah, we'll need to pass in the shaders as well. Cool. Alright. Then we'll create a new one of these. This new one, I'm going to use eval. In case there's an old value. We're just going to do the same thing. But case m old of nothing, pure, and just old release. Release old release. Okay. You're also going to need the render pass. Cool. Okay, 320. Pass the render pass. Great. Okay, we're compiling. Hopefully this should work now. Should be able to resize the window. There we go. Okay. There we go. Okay. Good. We're back. So, we'll call this, we'll commit this stuff. We'll call this like resize working. Swatching images. Cool. Great. Push that up. Good. Okay, yeah, so just to make sure, yep, if you want to follow along with commits, it's Sam BNT, Sam BNT RART, wrote. So github.com/sambnt/RART, and yeah, you can see that commit here. Cool. So that's great, but what should we work on next? Probably, we probably want to work on the buffer example. So let's uncomment that, get that working. So the buffer example is going to be a lot like the triangle example. Triangle. Sorry, I'm just gonna copy some code. So all of this is gonna stay the same. This is gonna change. So we're just gonna change the shaders and we're gonna change how we declare like what we declare. So the render step is only going to change in that we're changing our draw call, and the event loop is not changing at all. And what we're going to do is create a renderer, declare a new type of shader using the vertex buffers, um, vertex shader, and then we're going to declare our data. We're going to use a new thing called buffer where we tell it, declare like what the usage is going to be, and then what data is going to be in there and the size of the data. And the other thing we're going to do is make use of our vertex bindings and vertex attributes now. So just a few changes, not huge, but we will have to address a few things with our allocator because we've left parts of our allocator kind of undefined for the moment, and we'll need to fix that. So I think I'll take another break, take another 10-minute break, and we'll be back and get into that. So thanks for listening, thanks for your patience, um, and I hope to see you again in 10 minutes or so. Thanks, guys. Okay, almost back. All right, so what did we do? So we just got our triangle example working again, and then we made sure that we can resize the window. We got that fixed. And now we've just gone through what our buffer example should look like with sort of declarative interface where we're declaring, the shaders and the buffers um, and the vertex inputs and the draw call. So to make this work, first let's start off. Oh, yep, added that, so cool. So if we quit this and reload, should get a few errors, yeah. We'll fix those later. So the buffer, this is how it works at the moment. So it's taking the size of the buffer, so like how much data we're going to put into it, and the data itself. Um, and then what? Um, yep, we're deferring that computation, and then we're evaluating the buffer at some point here. And so what that's doing is it's getting this create info in the data, it's acquiring that data. So it's like um, we've told it how to acquire the buffer data, but we haven't actually acquired it. And now we're going to acquire it. Um, then we're going to get the bytes and put them into an array from an allocation. So the allocation in this case comes from this function with buffer, and that's going to create an allocation for us using Vulkan memory allocator. And we've got two types of allocation. Like if it ends up in host visible device local memory, then we call it device allocation. So essentially it's just allocated some memory on the GPU. We can write directly to it. Otherwise, like if the data is too big for the GPU or it just doesn't have the memory available, then it'll create the device buffer, but also a staging buffer. And we'll copy data to the staging buffer and then copy the staging buffer to the device. So yeah, just different types of memory. But we have a slight problem in that we're writing the data and then we're calling flush, but flush at the moment is undefined. Like we haven't really defined how that works yet. That's supposed to like flush the data so that the GPU can read it, but we're just not quite there yet. So what would that look like? Well, um, if it's a device allocation or if it's a staging allocation, it's pretty simple. So we just call flush allocation. We use the allocator and the alloc info. Yeah, we'll give it a type signature, monad IO, and just add the required language extensions for that signature. Okay. So that's going to flush the allocation. What's wrong there? Variable not in scope. Oh, yes. If it's a staging allocation, we've written to the staging buffer, so we need to flush that. You don't actually need to flush the device buffer. So the staging allocation, it's got the staging allocation in the first argument and then the device allocation in the second argument. So we're good there. That's fine. That's actually fine. Yep, so that's good. What are we going to do next? Okay, so if the device ends up in the staging allocation, we need to copy the data over at some point. So in the renderer, we're going to keep track of the data that we need to copy over. So okay, let's go to the renderer. We'll create a new what is it called? Member attribute. Call it pending writes. And it'll be a TQ of, let's call it buffer copy info. We'll define that here, buffer copy info. We've got a source buffer, destination buffer, and we've got regions. And we've also got a destination stage mask. This is for the pipeline barrier. Because if we are going to do a buffer copy, we need to insert a pipeline stage barrier to make sure that we're not rendering before we've written this data. Okay, that's not right. Boom. And the little data vector. Cool. But actually, just thinking about it, I'm pretty sure most of this will just end up in the device allocation anyway. So we might just be fine to ignore it for now. Yeah. Let's just get rid of that for now. Let's fix any errors. VK allocator. Context. And the alloc. Oh. Gonna need the offset and the size to flush, which is fine. What's going on here? Okay. Go to our buffer. And info, that shouldn't be there. Make frame data and record frame data, and that we don't need. Just import some things. Oh, yep. So we're gonna have to update our render types. So our drawers, instead of taking the vertex buffer, we're going to have a handle to a buffer, and the same here, handle to buffer. Actually don't need buffer ref anymore. Give that a reload. Buffer ref, get rid of that. Get rid of that there. Cool. And we'll call binary.encode on the vertices and the indices. So we're just encoding the vertices and indices as like a lazy byte string. Oh, and I'm going to need to import the binary package. Binary. Now we should be able to import this. Give it a minute to reload. There we go. Yep, gonna reload our cabal. So yep, we're just taking the vertices and coding them as bytes essentially, and then that way we can write it to the buffer. Load. Oh yeah, the validation layers. I'm gonna just turn those off for now, because like I said, my validation layers aren't working at the moment. Just some changes that I made. Oh, interesting. Be nice to have validation layers right about now. Just give it a minute for my computer to come back. Sorry about that. There we go. Okay, just had a crash. Cool. So something's not working. Let's have a look at render.hs. Eval buffer. All right. So that's fine. That's probably fine. I'm a little bit worried that the type of the binary encoding isn't going to match what Vulkan expects, but I wouldn't expect it to crash because of that. Just looking at my notes and see if I can find anything that might send me in the right direction. Blah, blah, blah. Oh, I mean, we should probably evaluate our buffers and then actually draw with them. That's probably a start. Okay. Submit. Let's go to submit. Cool. So, right. When we're evaluating the subpasses in the render pass layouts, we should try and just grab all of our buffers that are used in any of the draws, and we will evaluate them. So we're going to map M over the buffers and evaluate them. Why the pass input error? Okay. There we go. So that way we evaluate our buffers, and then what we're going to do is when we go to draw, we're going to make sure to actually use our buffers. It's a good start. So this will need a slight modification because we've changed the types for our buffers. If you've got any questions, please feel free to ask. Okay. So we've got handles now. So this is going to change a little bit. Going to get our draw vertex buffers. So going to get the vertex buffers that we're going to draw with. We're going to map over each of the handles and just get them because we know we've evaluated them already at the top of this function. And then we're going to unzip So fmap. So we've got a buffer, that's got a buff and an offset, and we're just going to put them into separate elements, or into a tuple basically. And that should give us the same types that we had before, which is just the kind of what we need for this function call. We need them to be separate. And then instead of a buffer ref here, we've got a buffer handle and then a deferred computation. And we are going to go index buff, offset, unsafe, get d. We'll make sure to import that. What's going on here? Oh, no. Going to import that. Yep. Okay. So now we should actually be drawing with our vertex buffers. Let's give that a go and hopefully we don't get another crash. Great. So we didn't crash, but we're not actually seeing anything. We can resize the window, but we're not seeing anything. So what we can do when this kind of thing happens, let's use vk render doc capture. I think that's what it's called. I think it's vk layer capture. So we're going to use render doc. We'll just reload and give that a go. Great. So now you can see at the top here, there's this, just some like stats, and it says like capturing Vulkan. So what we can do is we can jump over to render doc and we'll attach to a running instance, in this case GHC, and we're going to just press F12. That's going to capture a frame for us. We can double click on that capture now and go to our mesh viewer because that's kind of what I think is wrong. So like I said, the binary encoding of the vertex data is probably incorrect. So we'll check that out first. And then you just kind of like go through these one by one until you find what we're looking for. So here we go. Here's our draw. And you can see that this is the vertex input on the left. So, I mean, these indices aren't even right. This is the wrong indice. This is the wrong position. Like we've got two position elements, x and y. The first element x is 0, which could be fine, but the second element y is like a tiny number, and the color is made up of a tiny number and two not a numbers, and that's, yeah. So like basically we're just feeding it the wrong input. So, because I've just already kind of thought about this a little bit, what we can do instead is instead of passing in, really what all we want to do is poke this stuff into a pointer. And so instead of encoding it as binary, we can just pass in some sort of storable structure. So we'll leave that as is. And we're going to change the type of our render types. So this buffer info, instead of being a byte string, we'll call it, I know, A. So now the buffer info can kind of be anything. And here, in the buffer handle, we'll put like X. So for all X, storable X. So essentially like using GADTs, we can kind of have this witness that says whatever's in this buffer info is storable, which we'll make use of later. So all of the things that we should put in a buffer are storable. And then we'll just go ahead and follow the type errors. So render 215. Yep, so instead we should make this an A, and we should make this a storable A. Actually, let's make it a list. Oh, we'll just start with storable for now. Cool. And then 483. Yeah, okay. So we need to add a little like type signature here that captures that type variable. When we cast the pointer, we're going to cast it to an X, and then we'll just put the bytes. So this isn't bytes anymore. This is like a store, the thing to store. Just call it storable. Cool. And so poke array expects an array, so we'll just give it poke. Actually, no, we'll need to change that. So it expects an array. Storable poke array does. Like, so with storable, um, let's have a look at the documentation for storable. Let's open a new window and we'll look at storable. Cool. So foreign storable. This is essentially like just something for writing stuff to pointers, and you can see that there's an instance of storable for lots of the like default types like word32 and in our case float, which is like very useful, and you can write your own storable instances and that's fine. But if you look closely, there's no storable instance for an array. And we have like an array of floats that we want to store. So this is right. It's right to say poke array storable. And we really want this to be an array. But that means that we need to go back and change our render types again. So buffer info, instead of being an A, it's going to be a list of A. And everything else should be the same. Not quite. Yep, a list of A. Cool, there we go. So now we can just, instead of converting our vertices to binary, we just pass them in directly. So we can pass in any array of storable things. And hopefully that should fix our issue. Maybe we'll go back to using bytestring when we figure out how to do that, but for now, this works. So that's great. So if we capture again, and attach to running instance, you can see the difference. When we go to our draw call, you can see that the indices are correct now and the positions are correct. And as a result, we're actually seeing our, our triangle. Have a look at the thing. Not really sure how all this works, but anyway. There we go. Yeah, and you can have a look at what's rendered and stuff. So that's really cool. I really love RenderDoc. Great. So that's our buffer example working. I think we can resize the window fine. Yep. Excellent. So let's clean up any unused imports. So just a little bit of cleanup while we're here before we commit that work. Just bear with me. With swap chain. just getting rid of any warnings. Almost there. Cool. So call this working buffer example. So what we relied on there was that if we look at our allocator function, what we relied on was that when we call with buffer, it gives us a device allocation. But it can also give us a staging allocation. So we should really look after that example as well. Because if it did give us a staging allocation, we wouldn't have copied the staging buffer to the device buffer and our draw wouldn't have worked. So let's go back to our renderer. Oh, and add this again. So our renderer is going to keep track of the writes that are pending. So when we evaluate a buffer, it's going to write its data to the staging buffer in this example, and then it's going to record that, oh, look, I need you at some point in the future to copy this buffer over to the device buffer. So let's do that. We got pending writes. Cool. Okay. Got our pending writes. Come back to that. And it's all good. So when we evaluate a buffer, that's what we need to do. So we're gonna write our data, flush it, and then we're gonna say like, we're gonna ask the allocation, do you like need a buffer copy? Like, are you a staging or a device allocation? And if it says no, I don't require a buffer copy, we'll do nothing. But if it's like, yeah, and like here's the source and destination, then we say, okay, write to the TQ, STM atomically, write to TQ, the pending writes TQ. Is that what it's called? Ugh. Renderer pending writes. Cool. Then we're going to write our buffer copy info there. So the source buff, just call this source and destination so they don't collide. Source buff, the destination buff, the regions, just in this case a singleton of, so the region is, starts at 0. Oh, actually, what is that? Let's have a look at that buffer copy. Oh, this is the source offset and the destination offset. This is the size. Then finally, the destination stage mask. So we'll come back to that. That's going to be interesting. Cool. So this requires buffer copy. Put that in the allocator. Requires buffer copy. So given an allocation, we're going to return a maybe of the two buffers that should copy between. So okay. Yep, this isn't complicated. It's just if we've got a device allocation, we do nothing. If we've got a staging allocation, we've got our staging buffer, we've got our device buffer, and we just return those two. Just staging device. Cool. So that's okay. All right, this destination stage mask. So we should look at, actually we're going to need to pass in the renderer as well, because we're writing to the T key. So yes, the destination stage mask. So for example, if this was a vertex buffer, we'd want the destination stage mask to be like VK pipeline stage to vertex attribute input bit KHR. So essentially we're saying don't like read from the vertex attributes until we've written this buffer, because this is our vertex buffer. So like, yeah, please don't start drawing until we've written to that. But if this is an index buffer, like we don't need to wait for that stage. Let's have a look at what other stages we have. So we've got a bunch of stages. None, top of pipe, drawing direct, the vertex input bit, the shader bit. I mean, is there even one for indices? Oh yeah, here we go, the index input bit. All right. So you can see here, sorry, just, where was I? Yep. So you can see here, at the moment we specify in the vertex attribute bit. So this specifies the stage where the vertex buffers are consumed. So we want to write to the vertex buffers before this bit, and then this one is for the index buffers. So we jump back here. In our create info, let's go. So let's write a function that'll go from our BK buffer render types. So when we create the buffer, we're passing in some information, including the usage. So we want something that'll go from the usage flag bits to a destination stage mask, which is a pipeline stage flag bits or something like that. I think it's just pipeline stage flags. Okay. So we've got our usage and we'll be like, Hmm. If usage and we do this here and VK buffer usage vertex buffer bit. So if it's being used as a vertex buffer, then we, what do we do? Well, we say, okay, pipeline stage 2 input bit. Cool. Well, actually, let's make this a function. So this will apply the vertex attribute input bit if we're using it as a vertex buffer, else we'll do nothing. And we'll call this what, like vertex destination stage mask. And then we've got an index destination stage mask. It's the same sort of thing where if we're using it as a index buffer, then let's add the index attribute input bit. Is that what it's called? Blah, 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 index input bit. Else ID, and what we'll do, let's call this so we'll start with the VK pipeline stage to none. Is that what I want? Yes. So we'll just essentially have it at 0. Then we'll apply the vertex stage mask, and then we'll apply the index. So we start from 0, we apply these two functions, and at the end we should get either one or both of these input bits. And that'll be our destination stage mask. So make destination stage mask. Just use that here, and we'll pass in create info.usage. That should be okay. Oh, why is it not working? Oh. Okay. Just restart my Haskell language server. Come on. There we go. Ah, okay. Okay. That's looking alright. What's going on here? We need to pass in the renderer as well when we're evaluating. Okay, so that's good. It looks like we should be passing in our writes now. So any pending writes should get written to the queue, but we're not actually doing the writes yet. So let's write something to do that. So given a list of buffer copies to do and like a command pool to do it in, um, go ahead and do it. So if it's nothing, then we just don't do anything. But if we do have some buffer copy infos, well, yes, we're going to go ahead and do those. So what this looks like is like, um, we're going to have to check if we're running, if our graphics queue and our transfer queue are the same. And if they are, which like it's going to depend. On my case, like with my graphics card, it they are separate. But if they are the same, then we can just do a memory barrier and we add this pipeline barrier to the command buffer. Um, but if not, then we have to kind of submit to two different queues and just sync them up. So it's a little bit of work, but I think we're doing it in the right place. But for now, let's just call it undefined. And we'll put in the call to render buffer copies, record buffer copies. So right here, we're going to get the buffer copies. So stm atomically, tm then we're going to record the buffer copies. Because we're working with this little queue here, we're just going to do a bit of a mask. So we'll restore these buffer copies, but on exception, we'll make sure to write back the buffer copies to the queue. Because like if we fail to copy anything, like that's fine, but we should make sure to restore the previous state. And hopefully the next time it'll work. I mean, maybe there's no reason to believe it would, but we'll see. So for each buffer copy, we write it back. So it's getting a little bit messy, but that's okay. All right. So we first evaluate all the buffers, which should do all the writes, or should record all the writes. And then after that, we call record buffer copies. And if there's none, then we don't do anything. And if there is some, then it's undefined. But in our case, because we know it's a device allocation, we just happen to know at the moment, it should still work. But if it was to end up a staging allocation for whatever reason, it would throw an undefined error. So I think what we do is we'll leave it there and we'll um, come back to properly recording the buffer copies next time. It's been about 3 hours, so I think we'll give it a rest. And thanks so much for joining me. Like I said, these streams are available at youtube.com/@SamBennett_TV/ oh no, that's it. So you'll find the previous streams there and this stream as well. So thanks for your time and have a good day. See ya.